So we're going to talk about AC circuits again. We're going to look at it from a calculus perspective. And so let's get right into it. Resistors. Resistors are very simple from a calculus perspective because the relationship between voltage and current for a resistor is linear. There is no calculus to be concerned with. For capacitor, not so simple. A capacitor we had, and we've gone through the stuff on this slide previously. A capacitor, we define the capacitance as the ratio between charge and voltage. So Q is equal to VC is our definition for capacitance, just rearranged. And so if you take the derivative of both sides of that, you get dQ dt is C dV dt. Since capacitance we're assuming is going to be constant. We're not fiddling with our capacitor. And thus, by definition, dQ dt is current. So we have the current is C dV dt. So now we have a calculus relation for the capacitor. Then we, by the way, starting Thursday, we're going to start playing with chemicals in here. So once again, we'll need to not bring in food and drink and follow the rules that are posted. Because you're going to be teaching chemistry lab. By the way,
talking about because of physical science.
Yeah. I, by the way, won't be here Wednesday or Thursday, so we need to find a way to make this work.
Oh, that'll be fun.
It'll start with me talking to your math teacher.
Yeah, telling him I need to leave early.
Yeah. So let's look, right, because I'm going to California for the,
He doesn't take attendance, though, so you probably don't even have to talk to him. I can say that.
Well, it's still kind of disrespectful to just be like, hey, I'm out of here in the middle of lecture. So now let's look at an AC circuit that has a resistor and a capacitor. So just two things, simple circuit. And because they're in series, I'm just going to say we're going to put the same current through both of them. And so I'm putting a sinusoidal current. Does it have to be sinusoidal? Once again, no. But for our class, we just keep it sinusoidal and make life simple. So if I put that current through, what's the voltage across the resistor as a function of time going to be? By definition, V is equal to IR. And so that would be the I, which is I max sine of omega t.
What's the difference between little I and big I?
Okay, what's the difference? Little I is current that is changing. Capital I is a constant. So I max is a constant value, right? Because it's the maximum that's reached. Whereas little I is the current that's changing in time.
We have tests next week.
We have tests a week from today.
The other one almost graded. Because for some of us, it depends on what we got on the other one.
No. It is not. I have. It is the next on my grading. Yesterday, I had a whole lot of stuff going on, and then I took a little breather, and I didn't have my phone with me, and I didn't have a clock, and I completely missed my meeting with Alex. And then I was going to grade after my meeting with Alex, but I completely missed everything. So, yeah, I was going to grade this morning. Had a student in my office. We'll see how, don't have a TA, so I can't grade this afternoon. I want to get it graded. I graded the first problem and all the ones that are multiple choice. Okay, so sorry, that was an interlude. So we have the voltage cross resistor, which we usually would rewrite, put the R, I max R out front, and then put the sine of omega t. And then we have the voltage across the capacitor. Well, how do I find the voltage across the capacitor? Let me slide up to the previous slide. Yeah. We would have dVc is equal to I over C dt. And so I'm going to have to integrate that. And so what do we get for the integral of sine of omega t dt?
1 over omega times cosine omega t.
Now, I have to admit there's a little bit of unit variation here because I have dt. Basically, this is going to a limit of t, and that's the same as my variable. Let's pretend I just didn't break a math rule.
Wait a second, I did it right, but it's negative cosine.
Okay, I didn't even pay attention to the sign. Integral of sine is no. No, you're right. Right. The integral of derivative of sine is positive, so integral's got to be negative. So there we have that solution, and so that's equal to minus I max over omega c cosine of omega t. And then we say, well, how can we make this look more like the others? How can we make it a sinusoid? And so cosine of omega t, if I take cosine of omega t and I add pi over 2, I have sine of omega t. If I subtract pi over 2, I have minus sine of omega t. So let's subtract pi over 2 because we have the minus sign out front. And that's the voltage across the capacitor. And I'm going to go ahead and just change the color of this one because I can. So we've now found the voltage across the capacitor, the voltage across the resistor. What's the total voltage then across the power supply? According to Kirchhoff's law, Kirchhoff's voltage law, if I go up a Vs and then down a Vr and down a Vc, then I have Vs is equal to Vr plus Vc is equal to I max R sine of omega t plus I max over omega c sine of omega t minus pi over 2. Now, when you look at this, you have two different terms with different phases. That is, they're hitting their peaks at different times. And so what we do to get into the whole phasor idea is we say, let us pretend that we have, for the voltage, we have a voltage with this magnitude. So there's like VR. But that voltage with that magnitude is going to be going, that's the peak voltage, right? It's not going to stay at that voltage at all time. It's going to be going up and down, up and down, up and down. And so what I'm going to do is I'm going to say, let's consider the voltage that's in the horizontal direction to be the actual voltage. So I could take this and say, I'm going to rotate this about an axis, and only the voltage in this direction is actual voltage. So as it rotates around, I just take the component of this that's in the horizontal direction. So right now, it's all in the horizontal direction. But if it's tilted so that it's at some angle like this, it's still the same VR. But if this angle is, let's say, theta, then the amount that's in the horizontal direction would be VR cosine theta, right? And so as it goes around the circle, that voltage is going to be changing in a sinusoidal fashion as the angle changes. So if theta is omega t, then be VR cosine of omega t. Now, we actually use sine rather than cosine. So what we're really doing is taking the vertical aspect and saying the vertical aspect is the actual voltage. We always draw our pictures with it horizontal, but because I'm using the sine function over here to make it match, it's the vertical. But what's key is I can now take this voltage across the resistor and here's the voltage across the resistor. And then I'll put the voltage across the capacitor. And the capacitor is at a 90 degree, it's a different angle by 90 degrees. That's minus pi over 2, so that's why it's down. And then my total voltage is that, and it has some angle here that I find by comparing the magnitude of VR and VC. So I'll call this angle phi, and I would say tangent of phi is equal to VC over VR, opposite over adjacent. And so I can find that angle phi. And of course, V total is the square root of VR plus VC. And so that's what we're really doing with the phasors. We are graphing, essentially, I mean, that's the basis of it. Graphing the voltage across the resistor, across the capacitor, and saying, okay, only this projection is what the actual voltage is. The other projection is meaningless because the voltage isn't really going around in a circle. But because it's changing sinusoidally, we can use the circle as a mathematical tool. So that's where we get our phasor idea from. We take this here and we say, this is I max R with an angle of 0 because of the plus 0, plus I max over omega C with an angle of minus pi over 2. And so finding the total voltage using the phasor idea is pretty simple because you just have the Pythagorean theorem. So the total voltage is just the square root of I max R squared plus I max over omega C squared. So that's the maximum voltage we're ever going to have on the source. And then it's going to change sinusoidally. But notice it's not in phase with the voltage across the resistor. There's this phase angle phi between the voltage coming out of the source and the voltage across the resistor. The current was in phase with the voltage across the resistor. So that means the power supply's voltage and current are not in phase. The peak voltage is not at the same time as the peak current coming out of the power supply. A little surprising, huh? So that's a circuit with just a resistor and a capacitor. In case you're wondering about those little magenta numbers, 1, 2, and 0, the software I use to make this PHYS, put those on. Those are node numbers. Now the inductor. The inductor we've talked about very recently. We did not talk about it in calculus sense, though. We talked about it in non-calculus sense because we were in the general physics class. So Faraday's law of induction, the true law, is a calculus equation, which you probably had guessed already. because we have a continuously changing magnetic flux, we're going to have a derivative, not just delta flux over delta time. So Faraday's law of induction says the voltage across an inductor is minus N times the derivative of the flux with respect to time. And so just like we did in class yesterday, for an inductor, a self-inductor, we can calculate the magnetic field that's produced by the current going through it. And then from the change in flux of that very magnetic field it created, we can calculate an induced voltage. And so we define the inductance L to be this here. Now, if you look carefully, it's more clear if I erase what I just wrote. You'll see that there is something missing going from this to this. What's missing? The negative sign. Well, what did I say? And I noticed that our textbook does say the same thing. For once, me and the textbook are totally in agreement. What does it say that that minus sign's purpose is? Direction. It's there to tell us the direction. And so our direction has to do with that minus sign. So if we look at our sign convention is that if we have the current going and increasing, remember in class I only focused on this when I had the same slide. If the current is increasing, then we're going to assign positive to the side that the current entered from, negative to the side it's leaving from, and that sets our sign convention. That's where the minus sign disappeared to because we chose that for our sign convention. So now we're going to do the same basic problem, but now we have a resistor and an inductor. So what's the voltage across the resistor here if my current is the same current? I max R sine of omega t, just like we did before. And what is the voltage across the inductor in this case? How do I find it? That is a true relation, but not how I find it here, because I would still not know what it is, because I'd have to know what the relationship between Vs and Vr is. But I have this condition. And so I just have to do L times di dt. Derivative of sine is omega cosine. So there's my voltage across the inductor. Once again, I'm going to change the phase. Add the pi over 2 so that sine of omega t plus pi over 2 is cosine of omega t. And actually, we rearrange this. And there's the equation for a voltage across the inductor. Now you notice this one has a different phase, that is the sign has a different argument again. But now it's a plus pi over 2. And so if we do the phasor idea, we're going to now have a vertical going up for the voltage across the inductor. Something I didn't point out last time that I need to, you can see where that naturally came in. I'm not sure what I did yesterday, but you really need calculus to actually show where the omega comes into this. And so that we call the reactance for the inductors omega L. Up here, we had X for the capacitor was 1 over omega C because the current was divided by omega C. And so the reactances are found by doing the calculus. So now we have the simple circuits for voltage across the inductor, voltage across the capacitor. What if we put it all together? What if we make a circuit that has all three? Then what's the voltage through each element? If I have the same current in this circuit, what am I going to get for the voltages for each element? Going to be what? Okay, so that's going to be I max R sine of omega t, or in phasor form, I max R angle of 0. V capacitor, what should V capacitor be? Okay, we did the integral already, so I'm not going to redo it, but that's correct. We had to do the integral, and we found that it was omega c. Here I put xc angle minus pi over 2, and voltage across the inductor. We just did it. I max omega L sine of omega t plus pi over 2 equals I max XL angle pi over 2. So a test question on this. Now that's a very fair thing to bring up. If I'm going to have my test question on the RLC circuits, it's going to be something like, how do you find the voltage across the inductor if you have this current? Or how do you find the current through the inductor if you have this voltage function? Right, so it would require you to use either this equation or this equation. Right, because that's the actual calculus part. So now that we have that, I should have put more in my lecture. This is the last slide. I did want to cover Maxwell's equations, but I was like, there's no way I'm going to get that far. I will load it up in just a minute, and we'll just continue with Maxwell's equations. So now if we combine the three, which is what we're going to do in lab today, then we're going to have, using that phasor idea, a voltage across the resistance like this, a voltage across the inductor like this, a voltage across the capacitor like this, and then the whole system is rotating. And then we just take the projection in one direction to say this is the voltage at any given time. And of course, just going back to what direction do we choose, frankly, it doesn't matter. We generally choose to think of the horizontal direction. When they show these pictures in textbooks, they always show them tipped to remind you that the whole thing is rotating in time. And as we discovered, with one note, I can't rotate, so I can't simulate that here. And of course, if you add vectors, you add them tip to tail. And in lab, I am going to require that you do them in this order. Actually, well, first I'm going to have you add the VR and the VL like this. Because in lab, you're going to find that inductors aren't perfect. There are two things that make inductors not perfect. One is inductors are made out of wire that have a resistance that's not 0. So there's a little actual resistance in the inductor. If you measure its resistance, it's not going to be exactly 0. But more importantly, much more importantly, is our inductors are made with an iron core. They're made with an iron core because it makes the inductance much bigger for the same size inductor. But that iron core, you have to rotate the domains. That's taking energy. So there is energy lost in a real inductor because of the work to rotate the domains, which means that there is energy lost. That's what we associate with resistance. So there's an effective resistance to the inductors. Now, capacitors are pretty much ideal, but the inductors have an effective resistance. So when you do this, what you're going to actually find is that there is a little bit of resistance in the inductor that comes from that internal resistance. And so we're going to have our actual VR like this, the VL ideal, and then the V little r, and then we'll have the VC. And actually, the way I have you add them is, I think V little r, V L ideal, then V capital R, and then VC. The size of VL versus VC is going to depend on your frequency because XL and XC depend on the frequency. Okay, I am going to very quickly see if I can find, there we go. Oh, Google, why must you fail me? Yeah, thank you, Google. For some reason, the Google Drive file stream has some hiccups. Much more here on campus than at home, but this doesn't start up. It seems to be a big problem. Have you guys used Google Drive file stream yet? You have, yeah. It's actually a really nifty idea. Basically, you don't download the files to your computer. It takes your Google Drive as a network attached storage device. And so you're just working with files that are on Google's servers. It's a great idea. But in my office, it turns out to be slow. And on my home computer and this computer, it doesn't start up half the time. So here you see my full file structure. And where's that? Oh, shoot. That's not what I meant to do. Life is good. Minimize that. Actually, this will work. Maybe it'll work. It's supposed to have done something there. Okay, it crashed. That's what happened. Kind of worked. It's a good thing we're recording while I'm doing this. Okay, I'm going to do it in my office. I know it'll be dead time in the recording. What are we going to do? I'll be right back. My office computer apparently is more robust than the Surface Pro.
Would you offer to call them how this fits into different things?
Give me context before I take a stance.
So on my test, I got the question wrong, the sinus is follow space and not follow. Like that.
What's the difference?
No. Really, it's different.
I guess I could see So the sinus is defined as the hollow space inside, not necessarily the hollow space.
This is Dr. Seth was it reminding me as I was out there. Remember, you got the old pizza feed going on right now in Woods Auditorium as soon as class gets out.
Oh yeah, I forgot. I was gonna pay for food.
Why would you do that? And
Yeah.
the Da Vinci, okay, as long as it's, I forgot. The Da Vinci's 5-cheese pizza is amazingly good.
What am I required to do in order to get that pizza? Right? That's it.
You're required to walk in and pick it up. In the Woods Auditorium. It's a celebration for,
It's usually the atrium.
Hmm?
You get it in the atrium.
or yeah, you're right, the atrium. It's a celebration that, in theory, you've paid 100% of your school bill up to here, and now you don't have to pay anymore.
Where did they get that theory from?
I'm glad you started with the theory.
Well, yeah. I don't know about all y'all, but I know Alex's situation is clearly not that, and it's probably not that for the others either.
Oh, you got a full target?
I did not say that.
No, you did.
Yeah. So, Maxwell's equations. James Clerk Maxwell took a bunch of equations. We've learned a bunch of equations so far. What equations, what calculus equations have we learned so far this semester? Okay, we learned Coulomb's law as a calculus equation. What?
No, that's
Those aren't calculus equations. Those are important equations, but not calculus. Okay, Gauss's law, Faraday's law. Those are all four of the Maxwell's equations. At the time when Maxwell started his work, I think it was like 22 equations that they had to describe electricity and magnetism. And he whittled it down, and they whittled it down some more, and came down to just 4 equations that completely explain everything in electricity and magnetism. Furthermore, by combining those equations, he was able to show that electromagnetic waves, in theory, should exist. And so then experimentation done by Heinrich, he calculated the speed of these electromagnetic waves and found that the speed was the same as the speed of light in vacuum. And he said, based on that, that electromagnetic waves and light must be the same thing, which is about as realistic as saying Corso is running the same speed as that car, hence Corso is a car. I mean, that's the basic logic that he used. But Heinrich Hertz did experiments with light and with electromagnetic waves and found that Clerk Maxwell was right, that light is an example of an electromagnetic wave. So chapter 24 is a segue between electromagnetism and light, because light is electromagnetic waves. So we're going to look at that for the remaining few minutes here in class. Electromagnetic waves are waves made of electric fields and magnetic fields. And so here's a picture of an electromagnetic wave that will make more sense after we have looked at the equations. So here are Maxwell's equations in 2 forms, the integral form and the differential form. In the homework that you had to do, that calculus assignment, you used Gauss's law in the differential form for the one that had the electric field in the atmosphere finding the charge density. You use Gauss's law in the integral form for the cylinder and the spheres. Coulomb's law isn't here. Why is Coulomb's law not here? Yeah, Gauss's law and Coulomb's law they're redundant. They're really fundamentally the same basis. Just like we had Ampere's law and we had the Biot-Savart law, and they're not, only one is shown here because the Biot-Savart is really something that's fundamentally the same as Ampere's law, but it's in a more useful way of writing for some calculations. So the first law, Gauss's law for electricity, that says the flux, this side here is the flux, the electric flux, is equal to the charge enclosed divided by epsilon 0. Integral of rho dV is charge enclosed. I have epsilon 0 inside the integral there, but it doesn't matter because it is a constant. So that is just the charge enclosed over epsilon 0. So that's Gauss's law for electric. And like I said, you have the differential form as well. You have del dot E, and you're like, del dot E? What is del? Well, remember del is that directional derivative. And so it takes a little bit of work to move between the two. You can definitely see a resemblance between the integral and the differential portion or writings. I'm not going to go through how you transform through calculus from one to the other. But that's the first one. The second one is one that I told you existed, but that we never use. Gauss's law for magnetism. Gauss's law for magnetism says that the magnetic flux on a closed surface is 0. Why is it equal to 0? Well, the electric flux on a closed surface wasn't 0.
Because there's no
There's no magnetic monopole. You can never have a net magnetic charge enclosed by your surface. It's always going to be a net enclosed charge of 0, right? Unless somebody actually finds a magnetic monopole, which no one has ever done. So technically, you would have an integral over the magnetic, charge density. But what's the point if that magnetic charge density is always 0? Go ahead.
Would the magnetic monopole cause problems since magnetic fields are circular? Wouldn't it just?
Well, that wouldn't be the case if we found one.
But I mean, since a magnetic field is circular normally, you put a monopole in that magnetic field, wouldn't you just go around and around and constantly get pushed?
No, it would change the rule. The magnetic fields are forming loops because there's no magnetic monopole. But if a magnetic monopole existed, then they wouldn't. You could have radial going out magnetic.
Right, but what I mean is, shouldn't that monopole be affected as though, would it get pushed along the magnetic north?
Of
a normal magnet and a monopole, if they were to interact, would you just constantly get pushed?
It would. Okay, now I understand what you're saying. Not its own field. I haven't thought about that.
Be a problem
with perpetual motion.
Yeah, thermodynamics and stuff.
I don't know. We'll have to think about that when we have more time. That's new, unique thought I hadn't had.
Just seems like a great things.
Okay, then the next two laws, Faraday's law of induction. Faraday's law of induction was the electric circulation. That's not what we did in class. What did we do instead of the electric circulation? We said the induced EMF. So the electric circulation is equal to the integral of minus dB dt. Remember, we had in Faraday's law of induction the rate of change in magnetic flux dot dA. So this on the right-hand side is basically the same thing. It's minus the derivative of the magnetic flux. But instead of circulation, we had, or instead of the voltage, we had the circulation. But you know what you get when you do that calculation of the circulation? You get the voltage. If you have a closed loop, you're getting the voltage you'd have in that closed loop. So that's the integral form of Faraday's law of induction. Here's the derivative form. The differential form, you see it looks a little different. You got that cross product in there. And then finally, Ampere's law. Now, Ampere's law, or Ampere's law, as we English speakers tend to say, because that's the way we talk, is a little bit more complicated. When Clerk Maxwell was going through his work, he realized, and I will talk about this in class tomorrow, so I'm not going to spend time on it specifically today, but he realized that there was something missing in Ampere's law. So Clerk Maxwell did modify Ampere's law. He added the term that is the plus J. That J is the current density. And so he added Oh, excuse me, not the plus J. He added the first part. He added this part here, the part that has dE dt. What he determined was a changing electric field is equivalent to a current. And so that's an additional term. He called it the displacement current.
You don't have that in charge flow where there could be a magnetic field, a changing electric field.
Right. And I'll talk about this in class tomorrow, but here's the easy way to look at it. If I have a capacitor and I have current flowing from one plate and to the other plate, we could easily say, based on Ampere's law, that that's going to make a magnetic field that's going around these wires. But what about between the plates? There's no charge flowing between the plates. And so does that mean no magnetic field there? And he said, no, that wouldn't make sense, because all you have to do to apply Ampere's law is you have to say how much current is going through my loop. I can have my loop out here where I show that loop, but I could say, now I'm going to find where the current is flowing through and make my surface so it's going between the plates and the wire never cuts through my surface. So how much flux do I have going through that surface? I'm going to change the color so it's clearly. How much flux do I have going through that purple surface? 0. And so depending on where I choose to make my surface, I get a different answer, which is incorrect. And so he said, what we have between the plates is a changing electric field, hence the changing electric field must be equivalent to the current. So how much did Clerk Maxwell actually add to these laws? He only added a piece of one, but he had the wisdom of taking a large group of equations and bringing it down to 4. And so the 4 Maxwell's equations are very distinctively known as Maxwell's equations. Now, he derived that these supported waves, there's more than one way to do this, but this is the way that I wrote. Take the curl, that is gradient crossed or del cross, to both sides of the differential form of Faraday's law. So differential form of Faraday's law is this right here. So we're going to take that and do del cross on both sides. So there's my first step. Now I'm going to do the right-hand side because that part's pretty easy. The del operator is a spatial operator. It's partial derivatives with respect to x, y, and z. So that's not going to be affected by a partial derivative with respect to time. So I can freely move it in and out of that derivative. But moving it into that derivative, I have the derivative of del cross B, but del cross B is that. And so I'm going to substitute that in. Now, staying on the right-hand side is the easy part. The left-hand side requires a little more care. J is the current density. And so Maxwell said, well, let's just do this in free space. In free space where there is no current, hence no current density. So if we're doing this in free space, that last term is just 0. So I just right away say it's free space, the current density is 0, hence this is 0 in free space. So the right-hand side is now done. That's all the work we have to do on the right-hand side. Now the left-hand side, That's going to take a little more work. So let's go back to our instructions. Next, use the vector identity that del cross E is del times del dot E minus del dot del E. Okay, so we're just going to substitute all right, del dot E. We've got del dot E. That's equal to rho epsilon 0 over epsilon 0. And then del dot del. Del's a directional derivative. Del dot L is the second directional derivative. Just del squared. Once again, we're in free space. If we're in free space, what's the charge density? And so we're left with minus del squared E is equal to minus mu naught epsilon d second E dt squared, or just canceling the minus signs. We're left with this equation. Now, if you look at this equation, it may seem pretty unremarkable. But what this is a wave equation. The wave equation is del cross F equals 1 over v squared d second F dt squared. And so Clerk Maxwell says, whoa, I've got something that says the electric field, oh, I dropped a vector sign, excuse me. I've got something that shows that my electric field vector would set up an electromagnetic wave with a speed. What would the speed have to be if I compare these two? Compare these two equations. What does the speed have to be? Well, let's do the direct thing. What's in the, I have 1 over v squared in my wave equation. What's in that same position? So solve that for v. Obviously, there's a plus or minus. Nobody puts a plus or minus for the speed of light. And so he says, this is the speed, nice, the speed of an electromagnetic wave. And then you put in the values for mu 0 and epsilon 0, and you find, boom, it gives you the speed of light. And it's based on that he said the light must be an electromagnetic wave. All right. Go get yourself some free pizza.